There was a post on the Arachnus Integrators group whether someone could use 2 of the 4 SFP ports on an Arachnus 48 port switch to connect to another 48 port switch, and the other 2 of the 4 SFP ports to connect to a 24 port switch to provide higher throughput on the ports. So let's configure it. A link aggregation group, or LAG, is an instance of the Link Aggregation Control Protocol, or LACP, which allows the bundling of physical ports to act as one logical interface to provide a high throughput of what a single port could handle. For example, Arachnus ports operate at 1 gigabit. With LAG configured, we can assign any port to add an additional 1 gigabit port, thus providing a logical 2 gigabit throughput. But it must be understood to treat this as a motorway with 100 miles per hour speed limit. We can add another lane and 2 cars can go 100 miles per hour, but a single car cannot go more than 200 miles per hour. We're increasing the amount of traffic that can be carried through, but not the maximum speed. LAG also offers redundancy. If a port or cable should fail between the nodes, the other port will resume as a primary link and continue to operate at 1 gigabit. You can assign as many ports to be part of the aggregation group, but then you're using up physical switch ports to supply the demand for the extra traffic throughput. The network components I'm using here are the Arachnus AN310 RT4L2W router, an Arachnus AN210 24 port PoE switch, and an Arachnus AN210 8 port PoE switch. Let's set this up then. This is going to be configured at a switching layer, so I'll need to elect 2 or more ports on my switches to be part of the link aggregation group using the Link Aggregation Control Protocol, or LACP. On my 24 port switch, I'm going to go to Settings and Link Aggregation. Then I'll set LAG1 mode to LACP. I have the option of static, which when set sends the traffic evenly across the links and the ports are always active. One concern of this, however, is if you had a copper port connected to a media converter to convert copper to fibre and the fibre cable went wrong, the static lag will still continue to send traffic to the media converter because it still sees an end device at the end of that first copper cable run. So the data transmitting to the receiving switch on the other end of the fibre cable would fail and packet loss would incur. LACP evenly load balances traffic across the multiple links and sends an LACP protocol data unit, or PDU, along with a multicast group MAC address of 0180C2000002. If the receiving node also has LACP configured on the port, it will negotiate the PDU and understand that that port is part of a link aggregation group and send the packet in the opposite direction to form a single logical link. So if a port or cable fails on either switch and the LACP PDU is not received, the switch will assume there is a failure and the traffic will be transferred across to the working link. So we'll use LACP and set the member ports, in this instance, as ports 23 and 17. Before I make the physical connection, I'll go to my 8 port switch and set port 8 and 3 to member ports. You can also do this for the SFP ports too. And that's it. I make the connection and check that the lag is working. I can go to my 24 port switch log and I can see that ports 17 and 21 are up and the lag is up, and the lag is in a forwarding state and not being blocked by a spanning tree. On the 8 port switch logs, I see port 8 and 3 are up and the lag is up, and the state is set to forwarding on lag 1, so also not being blocked by a spanning tree. If I generate a ping to Google from my laptop on the 8 port switch, which is downstream from my router, and if I disconnect port 3, on my 24 port switch I'll see port 17 go out and I get no packet drops. If I reconnect and disconnect port 8, I will see port 23 go out, but I'll get a single packet drop, which would be unnoticeable to someone browsing the web. I have football streaming here on my other screen and the stream didn't drop at all. but the link has balanced over to port 3. You can also assign lags to a trunk port for VLAN purposes, so if you have an office with a lot of network traffic for instance, you can assign a lag to that VLAN to help enhance the throughput and avoid any potential bottlenecks. Another way we can test the link aggregation is doing a throughput test using Iperf. I have a Windows laptop on my 24 port switch, which I'll now set as the server. Unfortunately, the Windows laptop has only a fast Ethernet network interface card, so I'm not expecting massive throughput speeds. But if I send packets over a longer time frame and disconnect one link and another, we should see 1 or 2 packet drops. On this Windows machine, then if I go to command prompt and first of all type in ipconfig to get the machine's IP address of 172.16.25.108. Then in the command prompt, I will pivot to where Iperf is stored. So I'll do cd downloads. Iperf.exe-s. -s means server, and we can see that it's now in a listening state. If I go to my Windows parallel, which is on the 8-port network switch, and go to the location where Iperf is stored, right click and open in terminal, it will open a PowerShell window. I simply type in Iperf and hit tab when it will finish the command for me. I use -c, which is the client, so I want to put in the IP address of the server listening, which is 172.16.25.108. I then do a -t, which is the time, and I will tell it to do 60 seconds. If I press enter, it's now sending packets over the 2 links. And if I disconnect one link, we see a small packet drop, but immediately followed by packets back up to the 95 megabit mark. And then if I disconnect the other, I get the same result, proving we have redundancy. If I had a 2 gigabit capable network interface card on both sides, then I could up the data transmit size to 2 gigabit and see if we're getting any packet lost in transit. And again, prove these 2 1 gigabit interfaces are logically working at 2 gigabit. And that's link aggregation. If we were just to plug 2 ports from one switch to another without configuring link aggregation, we'd probably get a switching loop, and the network would eventually be brought to its knees, especially if spanning tree protocol wasn't enabled. If you did this and spanning tree protocol was enabled, which it usually is by default on Arachnis switches, you'd only benefit from 1 gigabit throughput, as spanning tree will listen for the loop and block the port from transmitting traffic onwards. So link aggregation is the correct way to link multiple interfaces together to form one logical link.